Hi, this screencast is on force. What is a force? Force is a push or a pull. It's a vector because it has a direction. Remember, a scalar just has magnitude, a vector has magnitude and direction. And when we talk of forces, we talk of direction. In which direction is that force pulling or pushing? A force is needed to set a body in motion. It causes a body to accelerate. Nothing will move unless a force is acting upon it. And as we'll learn, it only moves if the net force is greater than 0. The SI unit of measurement for force is the Newton, abbreviated with an N. And forces can fall into two categories. We have contact forces, where actual contact takes place. Our prime example is friction. Air resistance is a form of fluid friction and any physical contact. Non-contact forces, those are the magical forces of the universe. Gravity, electricity, magnetism, they will pull on you through their force fields even though they are not touching you. So gravity is this force of attraction between different objects, and there's a formula for it with a gravitational constant. But what's most important in this formula is that we can tell that the force of gravity is proportional to the mass of both objects which are pulling on each other. Anything with mass will pull on anything else with mass, okay? We don't notice it because you need to be really big. The force of gravity is very weak, and unless the object is much larger than you, you won't feel its force of gravity. But the force of gravity is directly proportional to the mass of the objects and inversely proportional to the distance. That means as the distance grows, the force of gravity weakens. As the mass grows, the force of gravity strengthens. And remember, weight is a force, and a force will change based on the force of gravity applied to it. So, the weight on the moon is less than your weight on Earth, whereas your mass remains the same. So here we have it. Gravity. Galileo discovered 400 years ago that objects will fall towards the Earth with a constant rate of acceleration, 9.8 meters per second squared. The unit of measurement for acceleration is meters per second squared. And as we saw in our lab, no matter what the object is, it's going to fall at that same rate in a vacuum, right? In a vacuum, when all air is removed, they fall at that same rate. And in normal life, we say, no, that's not true. It appears not to be true from our observations, because when we observe something falling, we observe something falling on Earth, and Earth has an atmosphere made up of a mixture of gases, okay, and they provide resistance. And that's what causes objects to attain a terminal velocity as well. When something jumps from a great distance toward the Earth, it will accelerate and start accelerating at that constant rate of acceleration, 9.8 meters per second squared. But at one point, it won't accelerate anymore. It will attain its terminal velocity, the fastest it can go, because it is being stopped by the fluid friction we know as air resistance. And the air resistance will increase its force as the object falls faster and faster until the force of gravity and the force of air resistance balance each other out. And as we saw, we tried the experiment on the moon. The feather and the hammer fall at the same rate. What is a centripetal force? Centripetal force is a force that makes an object follow a curved path. Its direction is always perpendicular to the motion of the object and pointing towards the center of the circle. So the Earth's gravitational pull acts as a centripetal force, keeping these satellites in orbit. Right? Anything moving around another object is being pulled towards the center of that object by a centripetal force. And what is friction? Another type of force, right? It's a contact force which resists motion. That's friction. It doesn't want you to move, okay? It always acts in the direction opposite to motion. There are 4 types. The first is static friction. If an object is not moving and you want to make it move, you have to overcome static friction. And that's the strongest friction there is. Then comes sliding friction. If something is sliding along a surface and you want it to keep sliding and not stop, you have to overcome sliding friction, which is weaker than static friction. Then you have fluid friction. If you're moving through the water, or you're moving over a fluid or through a fluid, which is a gas or a liquid, you have to overcome fluid friction. It's less than sliding and static friction. And then you have rolling friction, the friction which you must overcome if you're rolling over another material. It's also less than sliding and static friction. So here are some examples. If you try and push a box which is not moving, you have to overcome static friction. Once you overcome that static friction, it's easier to keep that box moving because sliding friction is less than static friction. A shark must overcome fluid friction as it moves through the water. And when you go sleigh riding, you must overcome sliding friction, which is less, of course, on ice. A wheel must overcome rolling friction as it rolls over a surface. We talked of the laws of Newton. The laws of Newton explain why objects move at all, right? We can describe how they move, their direction, their velocity and acceleration, but why do they bother moving at all? Well, Newton explained it for us. Newton's first law, the law of inertia, says an object will retain its position or velocity unless acted upon by a net external force. If you move in outer space in one direction, you will continue in that direction at the same velocity forever unless a net external force acts upon you. Newton's second law says there's a relationship between force, mass, and acceleration. If I increase the force with the same mass, it will accelerate at a greater rate. If I increase the mass with the same force, then it will accelerate less. And Newton's third law says for every action, there's an equal and opposite reaction. If you push on the wall, it's going to push back with the same force in opposite direction. Here's some examples of the first law. So if you want to increase the speed, you have an airplane going at the same speed. It will continue at the same speed as long as the forces are balanced out. If you want it to go faster, to increase that speed, you're going to have to give it some thrust. When you're in the car and you stop short, your body continues in the same direction. It does not want to stop. Inertia says it wants to continue in the same direction at the same speed unless acted upon by an outside force. That seatbelt's going to stop. The second law says force, mass, and acceleration are related, right? If you're trying to pull something with a lot of mass, you're going to have to apply a lot of force to attain the same acceleration as you would have if you were pulling something with less mass. And if you want to give that ball a lot of acceleration, you're going to have to apply a lot of force. And the third law says every action is equal and opposite reaction. You're stepping out of the boat. Guess what? The boat is going to move backwards. And since fluid friction is much less than sliding friction, chances are it won't give you enough resistance and you'll fall. When you fire a gun, it will recoil. That is the reaction. The action is the firing. The reaction is the recoil. So free body diagrams, what are they? We learned from Newton's third law of motion that every action has an equal and opposite reaction. In other words, forces always come in pairs. When drawing a free body diagram, we'll take into account the relative strength and direction of the force, as well as the opposing forces. Our goal is to determine the size and direction of the net force. This is the force that results from adding the forces together which are acting on a body. And when the forces are balanced, the net force is 0 newtons. When the forces are unbalanced, the net force is greater than 0 newtons, and the object will start to accelerate. Remember, we're only going to change the object's speed or position if we have a net force which is greater than 0. And when we draw these diagrams, we always draw them in pairs, these forces in pairs. Gravity pulls downwards. Well, if an object is on a table, there'll be a normal force pointing in the opposite direction of gravity. Okay, it's pair. If friction is pointing one way, well, the force applied when you push something over a table, you're applying that force, and your force is being opposed by the force of friction. So here are some examples. If I have an object, okay, and the force of tension, let's say it's hanging by a rope, is 1,200 newtons, and the force of gravity pulling downwards is 800 newtons, then the net force will be 400 newtons upward, 1200 minus 800. And guess what? That object is going to accelerate in the direction of the net force, so it's going to be moving up. In the second example, I have air friction pointing up, and it's exerting a force of 600 newtons. Gravity is pulling down with 800 newtons. Guess what? Gravity wins out with 200 newtons. Therefore, the object will continue to accelerate, increase its speed downward. And lastly, I have a box, right? And it's being pulled downward by gravity with a force of 50 newtons. The normal force is pulling in opposite direction with 50 newtons, so it's not going to go up or down. Those forces are balanced. But I have a force of friction pulling to the left with a force of 20 newtons. So it will accelerate towards the left because the net force is pointing to the left. Thank you.